Hello everyone. Welcome to the fourth lesson in your journey of learning calculus. As we are learning the foundation, functions play an important role. Proceeding from the third lesson, in this lesson we will learn few more important operations, properties, and how we can visually see them through graphs. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the fourth lesson on learning calculus. As we go ahead in learning the functions and different operations in functions which I have shown you in lesson 3, in this lesson first we will start with what are called combining functions. Now, like numbers, functions can be added, subtracted, multiplied and divided, obviously except where the denominator is 0, to produce new functions. So if we take a function, for example, f and g are two functions, then for every x that belongs to the domains of both f and g, we can write this kind of a notation. I will explain you what this notation looks like. So we define functions f plus g and f minus g as well as f multiplied by g, which is are defined by the formula this one and this one. So these are the three I would say formulas which defines how we can combine the function. So this is the lesson where we are learning the combination of functions. So note one thing, that this plus sign which is on the left hand side of the first equation, this represents the operation of adding the functions, whereas the plus sign on the right hand side, as you can see here on the right hand side of the equation, means addition of the real numbers fx and gx. And you have to remember one thing, that except where the denominator is 0, because otherwise this function will be something undefined. Now, as we use this f and g to use a combination of functions and we denote it in set notation, let us see what this set notation looks like. So if you start on the left hand side, this d of f, this actually represents the domain of f, which we have learned actually what is domain in the first, second and third lesson, is the set of all x values for which the function f of x is defined. D of g, or d within braces g, this represents the domain of g, that is a set of all x values for which the function g of x is defined. And if we take the combination of this is actually the intersection sign, as you know, in set. So it represents that it is the intersection of the two domains, which includes only those x values that are both in df and dg. So if I now take the element of x which is belonging to df with an intersection of dg, it actually means this, that x is an element that belongs to the intersection of the domains of the functions f and g, or we can say it in a simple language, x is a value that can be used as an input for both the functions f and g. Both the definitions are more or less correct. Now the question is that this particular set notation, why this equation is important and why we are showing it in a set notation. I'll just explain to you in the next part of the video. So as we continue with the combining of the functions, we can say that at any point of d of f which intersects of d at g, and obviously g of x will not be equal to 0, otherwise it will go undefined, we can also define the function f upon g by the formula of this. Now this requires a little bit of attention, which I will like to show you. This particular actually denotes it represents the value of the function of f at x. This denominator represents the value of the function g at x, and this particular f upon g of x, this is the ratio or division of the values of f of x and g of x. Obviously we have to take the factor where g of x is not equal to 0. So g of x is not equal to 0. Simply the reason is that 0 is undefined, as I now show you in the box. So from here what we can say is that x must belong to d of f intersecting with d of g, meaning x is in both the domain of f and g because they are intersecting with each other, and g of x is not 0 because division by 0 is undefined, and hence we can say the domain of the quotient function is this one. So this is a typical way of combining the functions and letting you understand how this happens. Now it would be better that if we can show you in an example. So let us take a simple example, f of x equal to x square plus 1, and this means that it is defined of all real numbers, which is this R, which means the set of real numbers. And we take g of x equal to x minus 2, also defined as real numbers, but remember that g of x not equal to 0. So from there we get the quotient function something as this. And so we know that f of x is defined for all of x, g of x is defined for all x not equals to 2, and the domain of the function is this one. Now as you can see, there is a slash kind of a backslash kind of a sign. This is what requires a little bit of attention. So first of all, R, as you know, this is a kind of a symbol which represents the set of all real numbers. So we are all dealing with real numbers, no imaginary numbers. Now this part actually is a symbol that shows the difference. So this sign represents the set of the set difference, and in this case it removes the specific value of x equals to 2 from R. That means it excludes the domain x equal to 2. So it will just include. So this is basically removing. That means it is actually showing what is called as the set difference. So from here what we can say is that hence x equals to 2 must be excluded from the domain of the quotient function. So more or less what we can say that the notation f upon g simply means taking the point-wise division of f of x by g of x, which is provided by the condition g of x is not equal to 0, and the domain ensures that the division is basically valid. So this is what actually is meant by the combining of functions. Now remember that functions can also be combined by using a constant, and we call this constant as c. So if I take a constant c is a real number of the function, then we can say cf is defined by all of x in the domain of c of x, which is this equation, and we can also write f times g, or a product of g, by this. So from here what we can get is a set of these type of rules. Now you can pause this video and take a note of this type of rules, because we will be taking one of the formulas of this rule and I will show you what are the further elaborations. So f plus g would be this formula, this domain, f minus g would be this formula, followed by this domain, and so on. Now we have added the functions through mathematical equations. I have shown you how the functions actually add upon. But the question is that it is always better to see this combination of functions through a visual effect. And that is what I'm going to show you in the next part of the video, how we can graphically add two functions and how do they look like. So the graphical depiction actually shows you adding two functions. For example, represented as y equal to f of x and y equal to g of x. So the key concept is that we add these two sums. So somehow you get we get a kind of a graph like this. Now I'm going to explain this graph one by one. So just hold on, as you can see. So first of all, let us choose a point A on the x-axis. So first is this y equal to f of x. Now this is what we call is the usual function. Now from here what we do is that find the y value corresponding to A on the graph of x. And this is represented by the vertical line segment from A to the point of the curve f of x, which is highlighted over here. Similarly, we find the y value corresponding to the A on the graph g of x, which I have just highlighted, this one. And this is shown by the vertical line segment from A to the point of the graph g of x. And now finally we add with this blue box, which I have just highlighted in this animation, we add the two values obtained in step 2 and 3. This is visually represented by the vertical line segment from A to the point on the curve f plus g of x, which is this one. So all in all, what we can say is that this is a method, it's a graphical method to understand how functions are added, and it visually represents the concept of combining the outputs of two functions at a given input. For example, if I take f of x equals to 2 and g of x equals to 3, then f of f plus g of A equals to this one, which will be adding to 2 plus 3 equals to 5. Simple. So we can add up to 5 steps above, and then we can show in a graph. So this is the same combination of functions, but it is shown in a graphical method. Let us see another example. Now, as I have told you just a few minutes back that I will take this table and I will take two formulas out of that. And what I'm going to do, I am going to take f plus g, which is equals to square root of x plus 1 minus x, square root of 1 minus x, and f times g, which will be this value. Now, if I plot a graph something like this, this is something which comes out of this value. Now, I am going to explain you one by one what I am trying to show you. Now, first of all is the blue curve, f of x equal to square root of x. Now, this is the blue curve. It is actually showing the square root function, which is starting at the origin 0 and as x increases and so on. Next, I come to this one. This is the yellow one, g of x equal to square root of 1 minus x. And it is also a square root function, but it is reflected, as you can see, across the y-axis and shifted 1 unit to the right. And it starts at 1, 0 as the and increases as x increases. Next is this blue one, which is the sum of f of x plus g of x. And here you can see that the green curve actually represents the product f of x and g of x, which is f times g. So the green curve actually represents the product of f of x and g of x, which is represented as f dot g. And to get the value, we add this one. This is the green curve. And from here, what we can say that this graph actually illustrates how to graphically determine the sum and product of sum. We have seen y equals to f plus g, and the product also we have seen f of x and g of x. How do we multiply that? Let me show it in a kind of a fresh page. Things will be much clearer. So as you can see here, the red curve actually shows the result of adding the y values of the blue and the yellow curve. This one, the green curve, actually shows the multiplication. F times g show the result of multiplying y values of the blue with the yellow curves at each value. And this graph illustrates how to graphically determine the same thing with the repetition, that the sum and product of two functions, how do they look like, and once we add the function and multiply the function in a fresh kind of a page. Now, there is another important thing which comes across function, which are called composite functions. These are extremely important in case of complex functions also, or complex analysis. Composite functions becomes very important. So just to tell you what is a composite function. So if I take f and g are two functions, so we define the composite function by f with a circle. Now this circle is not filled up. As you can see, it is just a kind of a circle, and it is defined by this kind of a function. And here we underline this g of x. This is called the inner function because it is evaluated first. So if we go by the composite function, remember that f of x is called the outer function, the left hand side, because it acts on the output of g of x, and g of x is basically called the inner function because it is evaluated first. So the composition or the composite function f with a circle g, what I am trying to show you, it actually means, number one, we take an input x. Second, we first calculate g of x. Then we use the result of g of x as to the inputs of f, and then we see the outputs of this composite function. Let me give you a very, very simple example to illustrate. For example, if I take this value f of x equal to x squared and g of x equals to 3x plus 1, then the composite function is something like this. So the step 1 would be to find out g of x, which I have calculated as 3x plus 1, and then substitute g of x into f of x, which gives the value of this, which finally leads to this one, f composite g times x equals to 3x plus 1 whole squared. Now this is again a mathematical kind of an example. How about showing this in a nice kind of a graphical manner? So f of g represents the composite of a functions f and g, which is this kind of a graph, this kind of a pictorial representation. Now let me tell you what it actually shows. It actually shows the composite function, but it actually also shows you how you can compute it. So we first start with this one, which I have just highlighted, input. We start with an input value denoted by x. Then the input value is first fed into the function g, which I have just highlighted. This function processes the input and produces an output, which is labeled as this one, g of x. So the output of the function g is that of g of x. It produces an output. It is then taken into an input for a function f, and the function f processes this input and produces a final output, which is this process takes the input and processes a final output, which is this one. So I mean to say this is a very chain reaction which takes an input over the function, produces an input, again takes the input value of the function f, and finally produces output. So that is why it is called composite function. So it applies one after the another. So function composition involves applying one function, in this case the first g, and then applying to another function, in this case f, to the result of the first function. So here you can see the notation f within brace f of g of x represent the composite of functions of f and g. It signifies that function g is applied first, followed by the function of f. Now similar kind of a thing, so here it is, the function composition involves applying one function g and then applied to another function f to the first function. Now I can actually represent this one in a much more simpler manner, which is this kind of a diagram. You see what happens. First we start again with the same x, we take an input value, then we go to g, the input x is first passed through g. Then it takes another function of g is the input for function f, and then it is taken as the final output of the. So this was a linear one. This I have put it as a kind of a cloud composition so that it looks better. So g of x, and then we get f composite functions of g, and it signifies that function g is applied first, followed by the function. Same representation, same concept of composite functions, but in a two different pictorial representation. Now from here we move to a very important topic, which is called shifting of a graph function. That means we can actually shift also the graph by vertical or horizontal, in way we will see now. So a common way, if you say what is the way in which we can shift, so common way of obtaining a new function from an existing is by adding a constant to each output of the existing function. So for example, if I make a vertical shift of the function y equals to fx plus k, that means what it shows, that it shifts the graph of f up k units if k is greater than 0. So this is now written, shifts the graph up if k is greater than 0, and it shifts also down if k is less than 0, obviously up and down. Now what about horizontal shifts? So horizontal shifts would be y equal to f within braces x plus h. Here what happens, that shifts the graph of f left h units if h is equals to 0, is greater than 0, and it shifts to right units similarly if h is less than 0. As simple as that. Now can we see this kind of a shifting in a nice simple graph with colors? That would be better. Here is what I am trying to show you. So this is a graph which typically, as you can see, it actually shows a parabola. Now how the shifting happens, let us go one by one. So this is the standard parabola, the blue parabola, y equal to x squared, and the parent function. So it is a standard parabola which originates at 0, 0. Now what I do first step is that we take a y equal to x squared plus 2. So I am adding 2. That means the red parabola is shifted 2 units upwards compared to the blue parabola, and its vertex is 0, 2. This one I highlighted in blue. So here it is, as you can see, it is shifted at 0, 2. Next I take y equal to x squared plus 1. That means this red parabola is shifted 1 unit upwards compared to the blue parabola, and its vertex is 0, 1. This one just highlighted in blue. Let me show you. Yeah, this one, and here it is the shift. So the vertex is now where? From earlier it was 0, 2, now it is 0, 1. Next third case we take is y equal to x squared minus 2. So here the yellow parabola is shifted 2 units downwards compared to the blue parabola, and its vertex is 0, minus 2. Here it is, it's 0, minus 2. So in this way you can very easily shift the graph of a function. I have taken a parabola, you can take any other equation. Now for example, if I take another y equal to x plus 3 whole squared, y equals to x minus 2. So I am adding 3 squared, as you can see it has shifted on the left hand side, and for the minus 2 whole square it is shifted on this direction. In a similar fashion, what I can do is that I can take this kind of a function, and here you can see what happens is that adding minus 2 to x in y equals to x, then adding minus 1, the result gives is something like this. So here you can see that as shifts the graph 2 units to the right and 1 unit, minus 1 means 1 unit to the down. So 2 plus graph 2 units to the right and 1 unit to the down. So in this way also we can do that. Now there is another important concept which comes. This is called shifting of the graph of a function. How it goes up and down is something which is also called scaling and reflecting of a graph function. Now you might be thinking that why these are important. As you will see when we move up to the calculus, these are pre-calculus preparations. These will also become very, very important. So in case that we are scaling and reflecting of a graph, so to the scale the graph of a function, for example, y equal to f of x, and to stretch or compress it vertically or horizontally, this is accomplished by multiplying this. So if I stretch it, if I compress it, I will basically be multiplying the function f, the independent variable x, by an appropriate constant, which is c, this one. And by an appropriate constant c. Reflection happens across the coordinate or special cases where c equals to -1. So there are certain conditions. Now I will just show you the conditions so that you can understand when we show the graph. So if I get c is greater than 1, then y equal to c of f of x stretches the graph vertically by a factor of c. If I get y equal to f of c times x, then it compresses the graph of f horizontally. If I take y equals to 1 upon c f of x, then it compresses the graph f vertically by a factor of c. And if I take y equal to f of x upon c, then it stretches the graph of f horizontally by a factor of c. So these are actually equations which shows the scaling of the graph. Further, if I take c equals to -1, then y equal to minus of f reflects the graph. And if I take y equals to f of minus x, then it reflects the graph across the y-axis. This would reflect across the x-axis. This would reflect the graph across the y-axis. Okay, so far so good. We will just show you, I will just show you few graphs so that it becomes important. So I will take the usual graph. Y equals to square root of x, and what I am going to do is that I am going to multiply the right hand side of y equals to x by 3 to get a kind of a value like y equal to 3 square root of x. It stretches the graph vertically by a factor of 3, and the graph shows something like this. Here you can see this is the original equation, y equal to square root of x. Here you can see it stretches. So here it is a stretch, and y equals to 1 upon 3 square root of x, it compresses. So this is what is called the stretching and the compressing. What about shifting of a graph when we take it horizontally? So the graph of y equals to square root of 3 upon x is a horizontal compression of the graph, I would say y equal to square root of x by a factor of 3, and this would be horizontal stretching by a factor of 3. Here again you can see simple, the same thing, y equal to square root of x, it is the original, and now we comes y equal to square root of 3x, this is the compression, and y equals to x upon 3 square root of x upon 3, this is what is called the stretching. So this is basically what is called the shifting of the graph of function in terms of horizontal. The earlier one what we have seen is the vertical. Okay, next what we see is that what is called basically the reflection. Reflection is something very interesting. So if I take a kind of a equation like this, so y equal to minus of square root of x is a reflection of y equal to square root of x. That automatically you can see right at the first go there is a change of sign. And y equal to square root of minus x across the x-axis and is a reflection across the y-axis. So you get this kind of a nice graph. Now let me explain you one by one what this graph looks like. Now first I come to y equal to square root of x. This is the standard square root function. It starts at the origin 0, 0 and increases as x increases. So this is the blue one. Now we go to the yellow curve, which is y equal to square root of minus x. And this function is basically a reflection of the standard square root function across the y-axis. As you can see, this is the y-axis. It starts at the origin 0, 0 and increases as x decreases. So the domain of the function is x less than equal to 0. And here you can see y equal to square root of y equal to minus square root of x. This is the red curve. And this function is again the reflection of the standard square root function across the x-axis. This was the standard reflection on the y-axis. It's the standard reflection of the x-axis. And it starts at the origin 0, 0 and decreases as x increases. And the domain of this function is x greater than equal to 0. And what is very important is that always this is not negative. Because number one what we get is that the square root function y equal to square root of x is always non-negative, reflecting the square root function. So here comes the next point. Reflecting the square root function across the y-axis changes the sign of the input of x, and reflecting the square root function across the x-axis changes the sign of the output of y. So this is a nice kind of a lesson. I hope you liked it, how the reflection changes, vertical, shifting, composite function and addition of functions actually looks like. So this is the one which is the square root function across the x-axis, and so reflection actually, obviously you can see the reflection on the mirror, how things actually change. So that's all. We will take a pause in today's video. Thank you very much for watching this video. If you have liked, please do not forget to subscribe and click on the bell icon to get all the notification from Physics for Students. And you can also write to me in this email ID. You can like and subscribe to my other channel, which is exclusive to Einstein's General Theory of Relativity. And you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue surprising you with more and more such videos and courses. Calculus, special relativity, modern physics will go on. But see you very soon. But till then, may the good Lord be with you.